My name is Igor Smolin, and I am going to talk about numerical simulation of the mechanical behavior of porous materials. This work was done by the group from the Institute of Science, Physics and Material Science of Siberian branch of Russian Academy of Sciences and Tomsk State University. Next slide, please. So here you can see the outline of my talk. Briefly speaking, I'll do some introduction about porous materials and modeling of them. Then we'll be presenting some approaches and example of modeling porous structure itself. Then the mathematical formulation of modeling deformation and fracture of these materials. Next step will be results of our computer modeling, and finally conclusions. First of all, when we talk about porous structure, we should pay attention to the different parameters which describe the porous structure itself. The first most known of them is the porosity, of course, but not often pay attention to other different parameters as for morphology or shape of pores and pore structure, specific surface curvature of this porous space, and so on. When we talk about modeling, we should pay attention first of all to the modeling of porous structure itself, taking into account the previous aspects. Then, of course, usually we try to model the effective properties of such porous materials, and then, of course, it is interesting to reproduce the aspects of mechanical behavior of such materials, including deformation and fracture. The first step, when we talk about the porous structure, I'll give here some examples of model structure which were taken from the papers presented here. These structures are based on statistical models, and here you can see two types of such structures, in which the first type is based on Boolean scheme, and the second on spatially correlated models. In my talk, I will talk about these structures. They are built using some random coordinates of some geometrical objects, for example, spheres or ellipsoids, which are placed in space using pores or space, or materials, for example, spherical balls. When we look at these structures, we can imagine that these structures can describe, for example, simple ceramics, and as for those examples, it looks like sponge bone tissue, for example. And again, I would like to mention that in my talk I will speak about these structures and think about describing ceramics. Here are some examples which we built using this approach. This morphology are named as overlapping solid spheres, or OSS, and this kind of structures, porous structure, is named by overlapping spherical pores, or some authors call it sweet cheese. When we look at the comparison of our model structure with experimental results, which were obtained in by our colleagues Siberian branch of Russian Academy of Science. These ceramics, zirconia ceramics, were obtained using nanostructured powders. And we can see that in reality we can found both morphology, which we describe by overlapping spherical pores, they are small ones, and overlapping spherical solid spheres, which are large ones. But taking into account that large pores maybe play more crucial role, we can conclude that OSS mimics sintered ceramics microstructure for these materials. That next step of my presentation is devoted to mathematical formulation. We used continuum mechanics approach, so we take the conservation laws of mass, equation of motion, and salvage of energy, conservation of energy. These are strain rate velocity relations, and the most important part of mathematical formulation is constitutive relations. Here we describe the elastic behavior by using hypoelastic formulation, the relation between stresses and stress rates and strain rates. And the second important point is that we took the approach of theory of plasticity, though we try to describe quasi-brittle materials, but it is widely used, for example, for rock materials. The nature of inelastic deformation different from ductile materials, but the approaches are rather similar. But to describe the so-called pressure-sensitive behavior of quasi-brittle materials, we use the plasticity function, which includes pressure, not only the J2. And to describe the so-called dilatation effects, the plasticity function and plasticity potential are different. The next important point, which takes relation to our session, is described by the damage accumulation. Damage is described by this integral and is based on strain behavior and influence the strength of material, namely cohesion. So just when damage approaches to unity, then material is absolutely destroyed. And this phrase reminds that such an approach, when we use pressure-sensitive materials, it allows us to describe the micropores, and when we, at the meso level, take into account pores explicitly, so we have into account two scales of pores. Some details of the mathematical formulation is presented in these papers in English. I have no slide about numerical approach. We used finite difference method, which is described in literature, and I don't pay much attention in my talk here now about it. The first example of modeling was uniaxial compression, and when we talk the three-dimensional numerical modeling, we can obtain average stress-strain diagrams. You can see that the approach which which I described in numerical, mathematical formulation, allow us not only to describe elastic behavior, but also descending part of this stress-strain curve, which is connected with damage accumulation and the influence on strength. To summarize the influence of pore structure on the average behavior, first of all, we study the influence of pore porosity and morphology on elastic properties. Here are plots of dependence of Young modulus on porosity. You can see that calculation for spherical pores give higher value of elastic modulus, but overlapping spherical solid spheres, they better agree with experimental curves which are presented here, and those green and blue curves are analytical models for such pore morphologies. Concerning strength limit, we can see also that spherical solids have better agreement with experiments than spherical pores. The experimental results are published only in Russian. But for those materials which I show you in picture previously, the correspondence is better just for those pore morphology. The second type of numerical modeling was simple shear. Again, you can see the stress-strain curves for that type of modeling of loading. You can see that the descending part of stress-strain curves are more longer in this case. And again, we can see that our calculations correspond rather well with experiments which we take from this paper. I forget to mention that for shear we have used parameters for not for zirconium ceramics but for aluminum ceramics. Finally, I'd like to present the pictures which show you damage distribution in calculated area. You can see that damage originate on the pores and they spreading like cracks, so we can say that this is some kind of modeling crack development in such materials. Well, with this I'd like to conclude and to say that the model structures created by combining overlapping spherical solids make well the porous ceramic materials produced by sintered oxide powders. These geometric models better meet the pore morphology of real samples. For example, for zirconia ceramics based on nanopowder material. And they give better agreement to the dependence of effective Young modulus and strength limit on the total porosity. And the application of evolutionary approach, which I am not talking about today, has provided a correct description of the formation of areas of high damage or cracks at the mesoscale and the influence of degradation of local regions on the material on the general nature of the stress-strain curve, including its descending branch. And I'd like to acknowledge the academic Mendeley Fund program in Tom State University, due to which which allow me to take part in this conference. So thank you for your attention.